Hi there. If the following free content proves to be useful to you, please consider liking the video, subscribing, and checking out the pinned comment down below for more options to support my efforts. Thank you for watching, and please enjoy the video. So what I'll do is, for the first couple minutes of the episode here, I'll be talking about the Liskov substitution principle. So let's hop right into that. So why won't you zoom in? There we go. Okay, so the Liskov substitution principle. So as I mentioned before, for starting on whatever episode 13, yep, that should be right. I've basically been going through each part of the S.O.L.I.D acronym. And S.O.L.I.D is, of course, a series of design principles. And what I wanted to do is, in 5 different episodes, just cover one of them per episode and kind of talk about them. And the principle that we'll be looking at today is the Liskov substitution principle. And this is, of course, now, the main thing about this is that these principles were developed by sort of a bunch of people working together, but in this particular principle was very well expounded by Barbara Liskov, and she designed it, or defined it very well in a series of papers and things of that nature, which I've actually started reading, not a behavioral notion of subtyping, but a different paper of Barbara Liskov. Unfortunately, it escapes me which one. And it's very interesting stuff that has to do with basically typing. So let's talk about the Liskov substitution principle. Now, the most important thing here is that unfortunately, a lot of the examples I found explaining the Liskov substitution principle in code are very contrived. They are scenarios where you kind of have to deliberately, I don't know, let's just kind of get into it, and maybe we'll kind of get to what I mean. But let's just start. So the definition, a more technical definition, and this is taken from a behavioral notion of subtyping, is, so if for each object, and that's supposed to be O subscript 1, but this IDE doesn't handle subscripts. So for each object, and we'll just say object 1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. Now, if you're wondering what the hell that means, that's totally fine. You know, this unfortunately, this stuff does suffer from the jargon. So I'll just kind of decode this top definition, and then we'll get into a simpler definition. But basically what this is saying here is, so for each object of type, so O1 of type S, you know, I'm not even going to try and decode that. Let's basically what it's saying is, don't make subclasses which don't have the same functionality of the superclass if they're expected to be used interchangeably. Kind of what it's saying here is, like, you've got, let's say you've got objects S which are a subtype, a subclass of type T. Your application, which is what is meant by this program's P here thing, P should be able to use objects of type S and T interchangeably, if, like, assuming they are subtypes and assuming they will be used in such a manner. Don't make subclasses which don't have the same functionality of a superclass. In other words, if they're expected to be used interchangeably. Now, you might be kind of thinking, as I am, like, isn't that kind of like self-evident? I think it is to some degree. So I'm actually going to use some of the code from the previous lesson, which was on the open-closed principle. That was in the previous episode. But basically what we had here is I showed you that the wrong way to kind of handle changing requirements. So for example, in the example before, I was writing a class called exercise. And since there are all kinds of different types of exercises, Like you could use a barbell, you could use a kettlebell, you could use your body weight. The wrong way to go about doing that is to create all this control logic here, and then so if barbell, blah, blah, blah. And a better way to handle that kind of variation, because I will very likely decide to add more kinds of exercises to this, is to use an abstract class or an interface, but in this case an abstract class works very well, some kind of abstraction. And so in that case we create this abstract class exercise. And for each type of exercise, we create sort of a specialized subclass, a subtype. So for example, we've got body weight exercise. And it's important to note that if we're doing this properly, all of these subtypes must be able to have the same behavior. They must be able to act in the same place as sort of our abstraction. They should all of these different subtypes of exercise. So we've got body weight exercise and we've got dumbbell exercise. All of these should be able to, by the rest of the application that's working on these objects, it shouldn't even need to have code to differentiate which these are. It should be able to look at them all through this abstraction and work with them through the abstraction. So basically, just to wrap this up, this isn't a long explanation here, but when you're designing these classes, your goal, let's say we have a case, like for example an exercise, where we have things that are very similar, but they might change in little ways as time progresses, as I add more functionality to my application. If the part of my program which is using these objects knows these objects, or like literally, what's the word I'm looking for, references them through an interface, it does not need, that part of the program does not need code to differentiate them. So what does that mean? Basically what that means is it actually will reduce the amount of code we need to write and reduce the amount of logic in those objects, because we're literally not writing this crap. Instead of this, all this stuff, we just have one print exercise data, which will return a string, and it'll satisfy the behavioral sort of contract there, but it's specialized based on what we need. So the contract here states we have a method called print exercise data, and it returns a string of exercise data. Now, the rest of my app doesn't need to know or care whether it's a body weight exercise that needs to do this sort of specialized code to create a well-formatted string, or maybe a dumbbell thing which needs to do other specialized sort of changes to that method. But everything gets treated the same by the rest of the program, and that is sort of my explanation of the Liskov substitution principle. Unfortunately, I did quite a bit of research on this, and it's just very hard to give good examples on it, because you have to like really deliberately do things in a way that you have to set up contrived examples for it to some degree. Anyways, hopefully I've explained that somewhat well, and we will jump into viewer questions.